This video will show how Alex and I created a self-erecting inverted rotary pendulum in both a real and simulated situation. We first modeled the kinematics of the inverted pendulum by creating a 2-axis robot simulation model. We used transformation matrices to convert points from one frame to another. The first transformation matrix was used to convert the points representing the first link from frame 1 to frame 0, and the second transformation matrix was used to convert the second link of the robot from frame 2 to frame 1, and then from frame 1 to frame 0. By plotting an animation of the robot's movement when given an input of theta 1 and theta 2, we were able to then model the overall work envelope of the robot. Due to the physical limitation of how link 2 is connected to link 1 at a 90-degree angle, the work envelope is a cutoff sphere. We then used the Lagrangian, the kinetic energy of a system minus its potential energy, to derive the equations of motion to model the dynamics of the robot. This resulted in one equation for each of the two joints. The equations of motion were then arranged into matrix form so that they could be used to estimate the theoretical physical parameters of the system. We learned how the physical parameters of the robot affect the dynamics by seeing how the theta values affected the movement of the robot. For example, theta 5 and theta 6 each respectively show the effect of friction on link 1 and link 2. So when these values were very large, the pendulum moved more slowly. We were able to validate the equations of motions we used by comparing the output of the virtual simulation to the output of the physical robot. The simulation shared the same waveform characteristics as the physical robot. We performed system identification using a Hamiltonian energy approach to estimate the physical parameters of the robot system using voltage, position, and velocity. The Hamiltonian is an operator that sums the kinetic energy of a system with its potential energy, and it was used to represent the dynamics of the system. The following equations were derived from the previously used Lagrangian equations of motion because the Hamiltonian is the same as the Lagrangian except for having negative velocities. The input energy was subtracted by the losses in the system due to friction when converting mechanical power to electrical power. Therefore, due to the law of conservation of energy, the input energy and loss was set equal to the Hamiltonian. We implemented a function to output the physical parameters of the system by converting the conservation of energy equations into a matrix form that would be able to calculate the 6 theta values from a data set of 10,000 points. To test the accuracy of using a Hamiltonian energy approach to estimate theta values, we collected data from our simulated robot to show that our function would produce the same as previously calculated theoretical thetas. We then used this function to experimentally estimate the physical parameters of the real system. We used an input of 2 sine waves to collect 10,000 data points from the real system and then calculated the theta values to be as shown on the screen. A digital selector was made by setting up a function to control a multi-port switch which would control the voltage supplied to the motor based on the state of the pendulum we were trying to balance. Originally, there were 3 settings: swing up, balance, and wait. However, once the system was working, a 4th reset stage was added that returned the system to the original starting location prior to initiating the swing up stage again. The inclusion of this 4th stage was important because by returning the position of link 1 is 0, the pendulum was better able to re-swing up and balance without lots of error in the Q1 variable. The system was set up so that it was only able to enter the stages in a certain order. These stages were selected using a function that took in the joint variable data in the previous stage of the robot and to then make a determination on which stage to enter into next. For the digital selector to accurately check the position of the link, it was important to normalize the data. Normalizing the data eliminated the issue of a position running off if it continued to move in a certain direction. This was achieved by taking the sine and cosine of the Q2 position to put through the arctan2 function. For the swing up stage, position logic was used to make sure that link 2 was at or near the bottom of the swing within a threshold which we set at plus or minus 10 degrees. Velocity logic checked that the velocity of the rod was within plus or minus 0.1 to ensure that the pendulum had proper time to settle and reduce variable error before swinging up. Additionally, there was a stage check to make sure that the previous stage was at stage 2. Once the swing up stage had been selected, gains determined experimentally through various trials were used to weight the Q2 and Q2 dot values, and they were then added to the weighted Q2 dot term to produce a desired position of the motor. This desired Q1 position was fed into controller to determine the error between the desired motor position and the actual motor position to determine how much voltage was needed to supply the motor. For the swing up to work correctly, correctly, the Q2 term had to be reset so that the bottom of the swing was set to 0. Similarly to the stage controller, this required the position to be normalized, which again required the use of Arctan 2. We could have alternatively controlled the swing up stage by using a Hamiltonian energy approach. The balance stage is activated as the linkage reaches the top position within a threshold of plus or minus 15 degrees. The balance stage calculates the voltage required to catch and maintain the vertical position of the linkage. It also requires a reset of the Q2 position so that it equals 0 when at the top of the cycle. To find gains that would balance the robot, we used the equations of motion modeling dynamics of the robot that we previously derived using the Hamiltonian. We then linearized the equations using the Jacobian and evaluated them at an equilibrium point where all the variables were equal to 0. We then calculated gains that would place all the poles of the joint variables on the left half plane. It is important to take note of the weighting of the poles. The gain of Q2 was by far the largest, since when balancing the pendulum, the position of link 2 is very important. The next most important joint variable was the velocity of link 2, followed by the velocity of link 1, and then the least important was the position of link 1. In addition, it was possible to balance a pendulum by using different values when placing the poles. However, the poles that we decided on were -5 because we believed that it created gains large enough to create a robust control of the robot so that it would better counter attempts to push it over. We were therefore able to successfully create a smooth and reliable swing up and balance from start as well as from being knocked down. The position reset stage is activated when the balanced pendulum is knocked over due to exceeding the threshold that the motor could balance the linkage. We set this to be plus or minus 25 degrees so that the system is more robust and trying to remain balanced. The wait stage is activated after the system has been knocked out of balance and it resets it to its starting position of 0. The wait stage provides 0 voltage to the motor to allow the system's energy to disperse before being kicked into the swing up stage to resume. To finalize the robot, we required it to move to a new position when in balance mode, follow a sine wave in balance mode, and also follow an analog input sensor. In addition, all these modes were supposed to work even if the pendulum was knocked over due to the addition of a fourth stage that we previously discussed. To implement a system which allowed us to control the position of Q1, we changed the system so that the Q1 term of the state variable vector was controlled by Q1 minus Q1 desired, so that the error drove it to move the system while maintaining balance. Overall, we were successfully able to perform all modes on both the simulated and real system.